All right, so the atmosphere, let's focus up front, please. The atmosphere is also much like the hydrosphere, possibly to a lesser extent, but is also one of the factors of the Earth that makes it very habitable. It does so in a number of ways. One of the main ways is that it does shield high energy radiation from the sun from the Earth's surface. And as I mentioned before, the atmosphere has not always been that way. It's not always had the high oxygen content that it has now. So some scientists theorize, and you may have seen the question in the pretest about this, that without the oxygen in the atmosphere that creates the ozone layer, we would not have life on land and everything, because the UV radiation and also the other high energy radiation would just basically nuke everything on the surface that wasn't protected by some seawater. So also the organisms, mostly bacteria, that lived before this took place would have to be a little bit further down in the water so that the water could shield them somewhat. So that's one major function. Also, being a fluid, it can absorb energy and move around, and so it distributes energy. And heat is the energy type of energy that it distributes. What was the other thing that ocean currents distributed besides heat, as it came up from the depths? Nutrients. Very good. Nutrients. Okay, so dust just seems like dust and dirt, but it's full of minerals, and that's one of the primary ways in which plants, both in the water and on land, get their nutrients, is from the wind blowing dust and everything around to them. And so that is a function. And you've also got pollen being spread too. That's a little bit more minor, so I didn't include it in there, but that's another function of the atmosphere that helps life on Earth. So that's what you wanted to be able to see there, the importance for life, and our main learning goal there. And then we have another phenomenon that is in our atmosphere that has to do with the type of gases we have in the atmosphere, known as the greenhouse effect. Now, this greenhouse effect gets a bad rap these days with global warming and global climate change, but it's actually a necessary thing for life. Well, it makes life, once again, much more easily livable, habitable, I call it, because it raises the temperature of the Earth to about 15 degrees Celsius, whereas if it wasn't, it would be below freezing. The average temperature of the Earth would be, so most of the water on Earth would be frozen. Obviously not something you want to have. So we can be thankful for the presence of greenhouse gases in our atmosphere that bring their temperature up as well. Composition of the atmosphere, the elements that make up the atmosphere, the main one is nitrogen gas. It is nitrogen in its elemental form, not combined with anything. The formula there is N2. It's a diatomic molecule. It's a very inert gas. So that means it doesn't react with a lot. Therefore, it's not particularly harmful or poisonous. Obviously, we wouldn't be able to breathe it in and out all the time for work. And it serves kind of to dilute out other substances which might be more toxic or harmful to us. One of which is, surprisingly, oxygen. It may seem strange to think oxygen could be harmful to us, but if it were in much higher concentrations, it would be physiologically harmful to us. But also, oxygen is a reactive substance, and therefore you would have chemical reactions going excessively, like the forest fires and stuff like that, because oxygen, of course, feeds flame and things like that. And so, although it's good we have the reactivity of oxygen, that's how respiration works, we don't want to have much more than we have now. I believe maximum oxygen levels that have been reached in the atmosphere of the Earth have been around 30%. That's when there was more plant life and productivity in general. And the fossil record shows that in those times you had continent-wide forest fires that would rage and things like that, and then things will recover, and as we'll see, fires. Not always a bad thing, but anyway, oxygen being a reactive element, really in the very early Earth atmosphere, once things cooled down and calmed down and the gases collected, those kind of things, there was not much of it because oxygen had reacted with the minerals, iron and silicon and calcium and aluminum and all those other kind of things, and consequently most of the oxygen is actually still in the crust of the Earth combined with other elements. Free oxygen in the atmosphere, elemental oxygen, O2, was pretty rare because, like I said, it reacted with other stuff and was no longer free on its own. It was combined. So the fortunate thing is that we have a process that does produce oxygen constantly, and that's why what we can owe our high levels of oxygen in the atmosphere to. And that process is photosynthesis. So you hopefully remember from biology that carbon dioxide and water are used by plants and other photosynthetic organisms, and they produce glucose and oxygen. Now, oxygen is actually a byproduct. It's not utilized by the plants. It's just excreted out in the atmosphere, but that's a good thing, not only for us to breathe, but as I said there, it forms ozone and blocks much of the high energy radiation from the Earth. So that's a very good thing. Probably actually more important than the part of giving us oxygen to breathe, because all the things that are on the surface of the Earth can survive now. Any questions? Any questions about the composition or some of the functions that the atmosphere of the Earth plays? Okay. You guys should not be on your phones right now. Please put them face down. All right, so the atmosphere is in layers, so you guys will want to pay close attention and study this some. From what I saw from the pretest, a lot of you don't know anything about this. That's okay. A lot of people don't. But as you know, or you should know, hopefully you know, as you go up in altitude, it gets colder. If you've been up in the mountains, you know this. It has to do with the fact that the air is thinner and therefore less able to hold heat. So that's a straight line relationship, the temperature decreasing as we go up into the atmosphere. However, at about 35,000 feet, which you would not be at unless you climbed out on the airplane wing when you're up cruising in a jetliner, and that would not be good. But the temperature actually starts to increase. So when it's that marks the boundary between the troposphere, which is the lowest layer, that's a layer that we exist in, that's a layer pretty much where everything that we're familiar with, weather, the greenhouse effect, air pollution effects, all those kind of things, those all happen in the troposphere, and that is where we are. And then after that, you have other layers of the atmosphere that are based on the way the temperature changes. And I'll show you a graph later. It's in the presentation already that can graphically show that. But the next layer of the atmosphere up is the stratosphere, and its importance is that this is where the ozone layer is found. The temperature does increase in the stratosphere. However, it doesn't get back up to like temperatures at sea level, but it does increase, which is different from what you get in the troposphere because it decreases as you get higher. Okay. And then that goes for a while, and then the temperature starts to increase again. That's what we call the mesosphere. And then it goes a little further, another 10, 20,000 feet, and you hit the thermosphere. By the time you get to the thermosphere, it's almost pretty much like being in outer space. Very little atmosphere, very little gases. So consequently, if you're in a shadow, if it's nighttime, the temperature is very low. Down like negative 200 degrees or so in those times. But then when you're in the sunlight, there's nothing protecting you, so objects that are in the thermosphere in the daytime basically reach up to 400 degrees Celsius, very hot, because they're getting bombarded by the sun's energy with no blocking of the atmosphere above them. So basically, troposphere colder, stratosphere warmer, mesosphere colder again, and then thermosphere warmer if it's daytime, colder if it's nighttime. All right, any questions about the layers? So you'll need to come up with some kind of mnemonic device or something like that to remember the order of them and what happens with the temperature changes, etc. And also the fact that the troposphere is where most of your action happens, the things that we're be concerned with, and then the stratosphere, the ozone layer occurs there. Otherwise, the mesosphere and thermosphere, they really are not don't have that much effect on us, so you won't hear much about them after that. Weather and climate is caused by the interaction of the hydrosphere and the atmosphere. So you think about that, the winds blow, the water condenses, precipitates, all those kind of things. They interact with each other to do that. The winds, the way that the winds form, we have it seems like the winds are always coming from different directions, but the fact is that we have steady winds, particular winds, prevailing winds they call them, like the trade winds we talked about with the El Nino effect. So there are certain wind patterns, predominant wind patterns that exist. These are based around the way the sun heats the atmosphere, and I'll show you all this in a diagram later on. But it's also based upon the fact that the air gets hotter at the equator, and therefore that hot air will move towards the poles through what we call convection, because convection takes hot air is a process by which a hot fluid, in this case air, moves from a hotter area to a colder area. It just kind of spreads out and moves that way, and that's a common thing to see in many physical systems. And so that's what starts the whole process of the wind formation. Then there's a whole bunch of other factors that affect that, such as Coriolis effect. You also have localized wind patterns that are affected by mountains and valleys and things, and also if you have land next to water, you'll have wind patterns that are formed by the fact that the land and the water heat up and cool down at different time periods. And once again, we'll study that more in detail later. And then you also have the season, and the seasons also affect the way the wind blows around, because basically the seasons, due to the fact that the Earth its axis is tilted, that means the focus of the sun changes every day. It goes between, basically the focus of the sun goes between the tropics of Cancer and Capricorn as the year progresses, and I'll show you a diagram to explain why that happens. But because of that focal change, bless you, not only does it get cold and hot, as you know, but also it means that it's pushing the atmosphere around when it does that. Kind of like if you had a laser and you're moving it up and down here, it would heat up an area and cause that area to move as you did it. The same thing happens across the globe as the seasons change. So those are correct in that bullet point. Very good. And then finally, you have air masses. This is what you'll hear referred to typically on a weather forecast. An air mass is a simple concept. It's just the fact that if you have air that exists over land and it's cold and it's near the polar areas, it's going to be cold and dry. If you have air that is over at the same latitude over a polar area but it's over the ocean, it's going to be cold and humid. And then if you have land that's over a more tropical area, if it's over land, it's going to be cold or hot and dry, unless of course it's over rainforest or some area like that, so that'll affect it. And then of course if it's over the water and it's near the equator, it's going to be hot and humid. And so those four different characteristics of the wind, of the air, may define a particular air mass. So why is that important? Well, those masses of air, they move around with the change in seasons, and then when they interact with each other, that's where the action happens. That's where you have weather occurrences. That's why like I said, you'll hear this on the weather forecast and everything. They'll say a cold front is coming in, for example. Winter is coming. So I can't wait. But the cold air masses, as they move down towards us, you will notice that it gets rainy and everything before you get that cold spell. Ever notice that? Remember that phenomenon? Okay. The reason why that happens is the cold air is coming into us. We still have some extra water vapor in the atmosphere and it's warmer, so that cold air causes that water vapor to condense, and therefore the condensation, the clouds build up and you have precipitation, and basically it freezes that water or condenses that water out of the air, and then once the cold air moves in and settles in, it's nice and dry and clear out and things like that. Because of that interaction. So it's where these different air masses interact with that we get our storm systems, and if that interaction, if there's a great enough difference to them and they're large enough, and you start to add in the rotation of what we call the Coriolis effect that we'll look at, you can get big storms like hurricanes and stuff like that forming. But this is also why hurricanes come at a certain time of the year, because it is driven by the change in the seasons as the focus of the sun shifts around. So, like I said, I'll go into more detail about that later and show you some diagrams and you know, like I did with the last set of PowerPoint presentation, the last PowerPoint slide, give you more details on that. Any questions so far? No? All right, very good. That is it for us for the day.